Swayam Prabha. Digital India. Educated India.
Hello everyone. Let's continue with the next topic. This week we will start with the controlling degrees of freedom, and we will see how we can control different degrees of freedom, how we can constrain it and then achieve the desired motion. So, as we discussed earlier, if it is a 3 dimensions, so any object has 6 independent degrees of freedom. I think it should be very clear by now. So, if you talk about any rigid body, a rigid object in space, in 3 dimensional space, the degrees of freedom are translation, 3 translations along x, y and z, and the 3 rotations along x axis, y axis and the rotation along the z direction. So, we are talking about the 3 translations along x, y, z and the 3 rotation along x, y and z axis. So, this should be very clear and we should not have any doubt. So, let us proceed. When it comes to 2D, when we talk about 2 dimensional case, and in many cases when we do the design, yes, we work with or we deal with the planar cases, and this is applicable, but in general I think we should be aware of both. In 2D case is easy to explain and easy to understand, and that is why we cover the 2D case and then we extend to 3 dimensional case. So, for instance, if it is 2D, then the object will have 3 degrees of freedom, 2 translations of and 1 rotational, and here again we are talking about the translation along x and along y axis. So, these are the translation we are talking about in the plane, and this is the rotation along the z axis we are talking about. So, perpendicular to the plane. So, it can rotate. So, again this should be clear to us, and when we are saying planar, what does it mean? It means the object is constrained or restricted to move in a planar surface only. So, there can be various means, we can talk about that as well, or many times it can be also constrained on the surface itself, the movement is constrained. So, for instance, in this case, just for illustration, I put this picture of whiteboard, so which provides the planar surface to these 2 objects. So, we have the marker and this duster, or what we can call it, the wiper. So, here we can define 2 axes, x axis and y axis. So, this duster can move in the plane along x and y, it can go anywhere, but at the same time it can also rotate. So, this is perpendicular to the plane axis, and this can rotate as well. So, again I think we should always remember, and if we have any doubt we should discuss, we should ask. why these kind of motions are happening, so that we should not have any doubt. So, planar case, 2 translational dwarf and 1 rotational dwarf. So, that is about degrees of freedom. What is constraint, and that is what I also mean controlling degrees of freedom, how we can control or how we can constrain. So, whenever we connect to objects, we will constrain them, we will constrain their motion. How? So, any object if we take and if we just put a pin, the relative motion is defined. So, and they cannot move freely with respect to each other. There are only certain degrees of freedom, certain motions that is possible. So, what we are saying, if you are putting constraints, applying constraints, and which is usually done by making different kind of mechanical connections, if you do that, the degrees of freedom of the object will get reduced. So, whenever there is a connection, highly likely there will be reduction in the degrees of freedom in their motion, and what we call that the object has been constrained. It is a restricted, the motion is restricted, it is a constraint. So, these are the terms we will be using very frequently, and we should always have an idea what we are talking about. What we also have to understand, moment we have any kind of constraint or any kind of mechanical connection between the two objects, there is always one-to-one correspondence between constraints applied to that object and the degrees of freedom removed. So, whenever we apply any kind of constraint or whenever we establish any kind of connection or contact between the objects, certain degrees of freedom will be reduced or removed. So, we have to always keep this thing in mind, that if there is a connection, if there is any constraint applied to it, the degrees of freedom will get reduced. So, very good. Very simple example here, like if we can just put a piece of paper and use a pin to tag on the board and just insert another pin here. So, this can also provide a constraint, and there is new term used which is called constraint line. So, there will be constraint line defined. So, along which the object will be constrained. So, this is what we call a device or means to provide the constraint, and what we are saying, points on the object along the constraint line can move only at right angles to the constraint line, not along it. So, whenever we have a constraint, so maybe we can draw another one, and what we are saying, maybe suppose we tag it here and then another pin. So, this is the constraint line, and this is the constraint or the device we can call it. So, what it says, moment we provide a constraint, the points on the object along the constraint line, any point you can extend, any object, it can be any irregular shape also. So, any point along the constraint line can move only at right angles to the constraint line. So, if this is the constraint line, the points here, any point we take, it can only move in the perpendicular direction, only that is possible. And any motion, if you want to give along the constraint line, that is not possible. So, there is no motion possible along this line, that is not possible. So, another way to make a mechanical connection between the two objects, I think we discussed earlier also. We can simply put a post here and there will be contact. So, moment if there is a contact or one contact is established, it can provide the constraint, and this is the constraint line in this case. So, what it says, regardless of which of these constraint devices we select, there can be different means to achieve that contact. It can be through a link, through a bar, or through a contact point. Regardless of whatever means we use, the remaining degrees of freedom are the same, they are not going to change. So, in this case, for instance, what we say, it can move along. So, any point on the line, it can move perpendicular to the constraint line, right. What it also means is, if we try to rotate along the z axis, which can be on the constraint line or passing through any point on the constraint line and perpendicular to the plane. So, we can choose any axis, and if we try to rotate, it is possible, because wherever that point may not move, but elsewhere we will have that tangential motion, the motion perpendicular to the constraint line, and therefore, that rotation is also possible. So, it is very important that this translation perpendicular to the constraint line and the rotation along the perpendicular axis passing through any point on the constraint line, that will be possible. It might be difficult to understand or visualize that, but if you try it, we can easily see, and we can start with placing any object against a contact point. So, we can create a post on the board, on the table, and then try to turn the object. So, translation is very easy, we can visualize, but rotation sometimes is difficult, and for that we can always create some experiments and can see ourselves. So, on the table, on the board, we can try and we can see. So, in this case, both the rotation and the translation are the 2 degrees of freedom, which will be always there regardless of what means we use here. What it also says that in this case, the body will have a rotational degree of freedom intersecting the constraint line and the perpendicular to the plane of the 2D body. So, that is what I was trying to explain. So, it can be, so it can also rotate here, so any axis, if we can take perpendicular, so perpendicular to the plane of the 2D body, right here. So, it has to be perpendicular and passing through the constraint line. So, you should pass through this constraint line. So, there will be always a rotational degree of freedom along that, and there is a translational degree of freedom perpendicular to the constraint line. So, that is what we mean. So, this is the constraint line. So, this motion always possible. What we also say that these 2 degrees of freedom are independent of each other. So, we can provide these 2 motions independently, they are not dependent on each other. Yes, there might be coupling in some cases, but these 2 motions can be always given independently. So, if we want to give translation, we can provide translation even without giving any rotational motion and vice versa. So, if we want to rotate without giving any translation at certain point, that also we can give. Yeah, elsewhere there will be translation and the rotation as well. But if we take the object, then what we realize there is an axis of rotation and there can be a translation as well. So, since these 2 motions can be made independently, since we can do that independently. So, it means we can provide 2 actuators and we can manipulate these objects, can manipulate the object using these 2 actuations, these 2 motions, and therefore, we have 2 degrees of freedom. So, whenever we are talking about what is the degree of freedom, in this case it will be 2, which will be the translation along, in this case, y axis, and the rotation along z. And what is the constraint? Constraint here is along this line. So, this is not possible, this is constraint. So, translation, what do you say, x, this is constraint, but the other 2 are possible and they can be given independently. So, in planar case, totaled of 3 constraints 1, and therefore, we have 2 degrees of freedom in this case. 1 constraint because of 1 contact. So, we can use some abstraction here and we will try to define what is a constraint and what is the best way to represent it. So, whenever we are trying to design some constraint device or want to design a system where we want to have certain degrees of freedom with the certain constraints, how to represent it. So, whenever we want to present a constraint, what we can think of a bar with articulating joints. So, we can always think of articulating means it can rotate anywhere. So, this bar, and you can articulating joint means think of a spherical joint. So, it is like more like a dumbbell. So, if you have so this can be defined as a constraint, and the constraint line is along the length, because we can always fix it and we can have another object a spherical. So, it is a spherical joint in 3D. So, that is what we mean. The bold uppercase letter C can be referred as C. So, we can always write a C to represent there is a constraint. So, this is a way to represent and referred in many of the books talking about constraint and degrees of freedom. So, when we extend to 3D, then we talk about 6 DOP. So, 3 translation and 3 rotation along x, y and z axis. Yes, here when we talk about the motion, suppose in x, we are talking about both the direction. It is not like a positive one off, negative one off, no. So, many times we face this issue and some people have this kind of confusion. So, if there we are talking about translation x means it can move both in positive and negative direction and is 1 degree of freedom. So, is 6 not 12. Same with the rotation, it can be clockwise or anti-clockwise, both ways. It is still considered as 1 degree of freedom. And if we understand degree of freedom and constraint, then we can talk about kinematic design. And so, what it says, design principle for imparting the required movements to a body by means of constraints. So, yes, there are 6 degrees of freedom, but the requirement might be for 1 or 2 or 3 or 4, maybe up to 6 also. And how we are placing the constraint, that is very important. And if we achieve the design using this principle, usually we call it kinematic design, and or we can also call it exactly constrained design. So, we are talking about minimum number of constraints here. Of course, for a rigid body in a space, there are 6 degrees of freedom in motion. So, any unconstrained rigid body, if you are talking about, it has total 6 degrees of freedom. So, always keep in mind. So, earlier we mentioned about contact. So, whenever there is a contact, we apply constraints, and one of the ways point contact leads to one constraint. So, a single degree of freedom constraint, if you want to use, we can think of a infinitely rigid sphere pressed against an infinitely rigid flat with the frictionless surface. So, this is what we are talking about. We can have a very large sphere and then a flat here and press against, so that we have only one contact made. So, if we look at this spherical ball and then pressed, this will be the point contact and this will provide the constraint. So, you can say this is the constraint line. What it also says that infinitely rigid sphere and infinitely rigid flat. So, here we are not talking about the elasticity or the stiffness, we are simply talking about the rigid object. So, any kinematic design is based on kinematic principles, and we assume that the bodies are not deformable, they are infinitely rigid, and then we talk about line contact or point contact, and so these are the ideal conditions. But it is a good way to start, because then we realize that we can achieve certain motions precisely, and we will be able to define the motions correctly, accurately. So, in this case, what it also says that this surface should be frictionless, no friction. So, it can slide easily, so it can move, it can slide. So, if you take this case, it can slide along the flat surface, right. Only one thing it cannot do is press against the surface. So, it cannot have this jet translation, but all the rotations also possible. It can rotate, except this motion not possible. So, it is a constraint along the z axis, or in general what we can say perpendicular to the plane. And we also talk about the nesting force. So, if there is enough nesting force, it will not lose the contact and it can slide or rotate or translate freely on the surface, making that contact. See. So, what we are just highlighting here, that a point contact imposes a single constraint. So, in general what we can say, that the number of contact points between any two perfectly rigid bodies is equal to the number of their mutual constraints. So, the contacts versus constraints we can simply add, and we can always use this analogy to model. So, models for predicting the motion of a mechanism can be then constructed in terms of number of contact points only. So, we can just think of the number of contact points, and we can use this geometrical abstraction of spheres connected by rigid links to design any kind of mechanism. So, in this case, a spherical object resting on a flat surface. So, the body has a single point of contact, and the only movement, that is in z direction, is a constraint. So, many times any kind of constraint if you are putting here. So, if it is dotted, it means constrained. This motion is constrained. So, that is why you see the z translation is constrained here. Rest all the motion if you try to do. So, along x, y, z is not possible. So, translation possible, the rotation. So, for instance, here this rotation and even this rotation also possible. So, in case the degrees of freedom, if we talk about, that is 5, out of 5 we have translation, 2 translations, that is x and y, and 3 rotations along x, y and z axis. Similarly, if we extend the same concept and just start designing devices or links or components. So, 2 contacts. So, for instance, if we simply take a link, any object, and then rest it on the surface. So, here is a dumbbell shape, or what we can say 2 spherical balls connected rigidly. So, 2 degree of freedom constraint. So, we want to define 2 constraints, and how it can be constructed? We can use 2 spheres joined together to make a rigid body. So, they are connected rigidly. It can be connected by any means, but here we simply say okay, this is how it is connected and placed on a surface. So, any object if we take and try to put on the surface, if it is making only 2 contacts here. So, These are the two constraint line we are now talking about, C1 and C2, and these are the constraint to contact points. What happens in this case? Again, if we place it in on the surface, flat surface, what we will see is it can move in x direction, can slide easily. Again, it is a frictionless surface, so it can translate in x direction. Similarly, it can move in y direction. So, in x, y we can move it very easily. What are other things possible in this case? So, suppose just take this thing in this configuration. So, try to rotate x we do not take now, but try to rotate along y. So, yes, along y axis it can rotate. So, we just put it there and try to rotate, it can slip at the contact point and can slide and can rotate, or we can do both, it can roll also. So, that degrees of freedom is there. So, x translation achieved, y is also possible. Rotation along y axis, that is b, that is also possible. What about the z rotation? So, if you are talking about this rotation c, that is also possible because we can turn without lifting it. So, we still have those two contacts C1 and C2, but we try to rotate along z axis which is perpendicular to the plane, we can still rotate. So, that is also possible. What is not possible? What are the constraints here? Yes, both are in z direction, C1 and C2. So, of course, this is the constraint, this is the constraints, not possible z translation, because only with only if we allow lifting, and so we do not have any contact anymore. So, there are no constraints. So, it is not a valid choice. So, or if we press, yeah, means it is infinitely rigid. So, it will stop the motion and then there will be no translation along z axis. So, there will be constraints. So, along z it cannot move. What about the rotation A? If we try to rotate along this. So, in order to have that motion, so anywhere we can take that axis which is parallel to x. That is possible only if we for some reason remove one of the constraints or one of the contacts C1 or C2, otherwise it is simply not possible, either it will impinge on or leave the surface. If we try to rotate this way, this will impinge and this one C2 will lift up. So, again it is a not valid solution. So, it means this rotation again are constraints. And previously also we mentioned, whenever there is a parallel constraints, linear constraints, they will always constrain a rotation which is perpendicular to the plane. If we just take those two constraint lines C1 and C2 and make a plane out of it, then if we take if we try to rotate the object along that axis perpendicular to that plane, if we make a plane, so it is a constraint plane in a way. This is not possible. So, two contacts, two constraint, and we have total number of degrees of freedom here 4. So, that also we get if we say for general body is a 6 minus 2 constraints or 2 contacts. So, contact versus constraints is the same, and we are left with 4 DOF, degrees of freedom, and which is in this case the 4 DOFs are 2 translations and 2 rotations. If we extend the same concept and now we connect 3 spherical balls rigidly. So, we made a connection and we connect them. So, what happens in this case? We have now suppose C1 here, call it C1, C2 and C3. So, now there are 3 parallel constraints, and one may has to remember that this, if they are in a line, then we have a difficulty. But moment they are placed elsewhere and they do not fall on the same surface, then we have 3 constraints. And if we, so 3 contacts. So, in general 3 contact means we can also say 3 constraints. Why we are saying in general is because we are not talking about the over constraint design yet. So, that will take up and we will try to. So, for instance, here when I mentioned three parallel constraints on the same plane, or if the point of contact are along the same line, then we have a difficulty. So, those cases are like we are not talking about those cases currently, and we will understand, and as we move on we realize that those are the over constraint cases. So, if we have 3 constraints, 3 contacts, and if each contact removes one degree of freedom, it means we should have DOF 6. If it's freely moving in space, it will have 3 DOF. We remove 3 of them and we are left with 3 DOF. So, we need to understand here what are the constraints imposed in this case and what are the degrees of freedom. So, for instance, again is on the flat surface, right. So, translation x DOF is a DOF, that is translation x. I think it can slide, the entire thing we can simply slide along the x direction without leaving the surface. So, the contacts will be still there. So, it means the translation x is there, that degree of freedom is there. What about y? Again it can slide. So, again it is a DOF and that is translation y. So, 2 translations possible, z of course not possible. So, 2 translations DOF along x and y, we are left with 1. So, if we try to rotate along the z axis, that's still possible. So, rotation z axis. Again it's a DOF, it's possible, right? Without, so on the surface we can do. So what we see here, if we have three contacts, actually we have established a planar constraint. It can move on any plane, moment we have three constraints. What are those constraints? So, rest are like rotations. So, these rotations again, I think I put a x is getting confused with the x, or what, maybe I may have to choose some another notation. So, yes, not possible rotation because it has to lift. So, it has to lose one of the contacts if I define. So, I can also like align one of the bar along the x axis and try to rotate, then we see that the C3 is leaving the contact. So, it means it is not possible. So, this is not possible. What about B? For B also we can align one of the bar and then we can see the C2 is leaving the contact, and or we can always generalize, and here again this rotation is also not possible. So, rotation x, rotation y not possible, and translation z also not possible. So, what exactly we are getting is, yeah, here if is one rotation. So, these are the 3 degrees of freedom and 3 constraints we have, planar constraint we have established. And that is the reason when we are talking about the 3-legged table or 3-legged chair, they can move in any plane, it can be a virtual plane. So, if we just take those 3 contacts, we can always define a plane. There is always one plane defined. So, it is identical, not identical, I would say it is a unique C1, C2 and C3, and a plane can be defined, and along that plane it will be always stable. And that is why we are talking about the 3 contacts, 3-legged chair, 3-legged table. Moment we have 4, we have trouble. C4, how to make that contact? I can put another ball, but then I have to make that C4 point on the same plane, which means added constraint or added tolerances to the component, which means higher cost. So, I think if we are able to understand the contacts and constraints and how it provides us the suitable constraint, then we realize putting one extra constraint is always a costly affair. It brings a lot of redundancy, and later we find that if we try to constrain using that extra contact, then it will also develop stresses in the system, internal stresses, which may not be desired if we are trying to develop precision systems, because these internal stresses will also give rise to deformations, and suppose the measurement and those things are also on the same frame, we will have issue with the measurement as well. So, there are several examples. So, for instance, what if they are done differently, if it is not flat surface. So, for instance, in this case, instead of putting a ball on the flat surface, if we put on a V groove, what will happen? So, moment we put this sphere on the V groove, now we have 2 contacts. So, 2 contacts means 2 degree of freedom constraints. So, because we can always define 2 constraint now C1 and C2, and this ball can rotate. So, it means 2 constraint we should have 4 degrees of freedom. So, it can move along the groove which is x, right. Y and Z translations we will see. What about the rotation? Rotation is possible, it can rotate along x, along B also possible, C also possible. So, rotations we do not have doubt, it can just slide and can rotate in all the 3 axes. What we are saying is they will not move along C1 and C2. So, it means any frame we define on that plane, but we can define here y and z axis, and what we can easily say that this point will not move, and if it does not move along C and C1 and C2, it cannot move along y and z as well, because we can always have some kind of this thing. So, we can resolve the component and we can see that those motions are not possible both in y and z direction. So, these things have to be checked carefully, but again here 2 contacts means 2 constraints, and those 2 constraints are in this case y and z translations. So, it cannot move, and those are basically, if we are talking about this V groove, basically we are talking about these translations. So, these are the constraints. Likewise, we can with the single spherical ball also we can have more than 2 contacts. So, if we put on a trihedron hole, so it will make 3 contact here. So, now and that way we can, so it is very difficult to visualize, but maybe what we can say is so one surface, second surface, 3 surfaces, and they will all pass through same point, and actually this point is now located C1, C2 and C3, and now in this case all the 3 translation will be constrained and we will have only 3 rotations possible, and in a way if we put this way, actually we create a spherical joint, a spherical ball joint. So, we do not need to have a cup and cone structure. So, in most of the cases what we usually think that we have a spherical ball, we need to have a conformal, a spherical surface to hold it to create that kind of joint. But if we understand contact and constraints and the kinematic design principles, what we realize that simply placing the ball on a tetrahedron hole will also give me the same function, and we should be able to create the spherical ball joint. What if we take a link with the 2 spherical ball and put one on V and one on a flat? What kind of constraint we create? So, here if we see again C1, C2 and C3, and if you try to analyze, we will see that yes, again is a point is constraint. So, what we realize, what are the degrees of freedom is, it can translate, it can move along V, along the V direction, because in the flat it does not oppose any motion along that translation motion. So, this is one DOF. Another is this rotation, if you want. So, if it is passing through this, or even otherwise, if we just try to rotate, the orientation of the bar will change, and since the flat does not oppose any constraint in this direction, so it can slide and can reorient. Therefore, it is also possible to have Z rotation. So, we will have that in and out motion, and we can have that Z rotation as well. So, again 2 DOF here. So, 1, 2, 3 constraints. We said 2 DOF. Where is the additional one? We need to have 3 DOF. Another one is just the rotation along that axis. So, it can rotate. So, plus 1 rotation along the axis itself. So, 1 more DOF. So, total 3 DOF. So, 1 translation and 2 rotation, one is along the plane and the other is along its own axis. So, there are various methods to create trihedron hole, trihedral contact. It is very difficult to manufacture. So, some easy way. So, you can simply place 3 ball, a spherical ball, and weld it, and then place the 4th one on top of it. So, this is the 4th one, and it will sit on those 3 balls and make 3 contacts, or we can use some kind of machining method, ingenious method. So, we try to create the surface and then crisscross along 120 degrees, and we will be able to create the surfaces. So, this will be the surfaces, trihedron hole, and we can place it. So, not necessarily we have to exactly make the trihedron hole, but we have to mimic it. We have to create these surfaces where it is making contact. So, in this case here is made by these 3 landing surfaces. Here is made using 3 spherical balls. So, what we realize, we can design many mechanisms for different kind of constraints. So, we can place 1 constraint, 2 constraint, 3 constraint, and we can always use a spherical ball on a flat. How many contacts will be required, and accordingly we can place those many spherical balls and rigidly connect them, and we can create different designs with a different number of constraints. So, we will take these examples like 1, 2, 3, then how we can get 4 constraint or how to get 5. So, we will be discussing these constraints one by one in the next lecture, and we will take some more examples, some examples we made with the 3D printed objects, and I think it will be well understood, and we will be able to design things using these concepts. Thank you.